let's get started. So welcome everyone. Good morning, good evening, good afternoon, and good night for wherever you are. And thank you for joining us for this live art session. So my name is Marin Cornec. I'm currently research engineer at the Laboratory of Oceanography of Villefranche-sur-Mer in France. And I'm basically working on using BGC Argo flows data to study the dynamic of phytoplankton, especially in layers below the surface. So I will make a brief introduction of the live session. So first, a quick presentation of the team members of the air session, then a global presentation of the Art Toolbox and how to reference it, then present rapidly how is constructed the synthetic file indexed, which is used within the Art Toolbox. A quick reminder of the data modes for the different parameters and files, and just a reminder of the help desk functioning solo station, and then we will start with the live session directly. So, okay. I will present our team. So myself, it's already done. We are here with Yibin Wang, who is a postdoctoral fellow at the NOAA at the PML laboratory. We have Raphaël Sauzed, who is working at the Institut de la Mer de Villefranche-sur-Mer. Quentin Jutard, who is a research engineer at Sorbonne University in France. And finally, Catherine Schmechtig, who is a research engineer also at the Sorbonne University. And so all of us worked all together to traduce and adapt and develop the air package that we will use today. And this package was translated and adapted from the BGC Argo MATLAB Toolbox, which was developed by Helmut Frenzel, John Sharp, Andrea Fassbender, Josh Plant, Tanya Moher, Yui Takeshita, David Nicholson, and Alison Gray. So just a quick presentation of the Art Toolbox. So this will provide function that will allow to access the file of the BGC Argo floats data to basically process them, and a few tools to visualize figures to see either section or profiles or trajectories distribution. So you can access to the toolbox on the GitHub repository. So here you have the link. And so using this link, you can either access to the code by cloning the repository to your desktop, open it with the GitHub desktop application, or directly download the zip code in one file. And before using the functions on air, be sure that you are working in the good repository, the one that you placed the files in. And so we work during the development of the toolbox. We work with the Air Session version 3.4 and the Air Studio version 1.4. And so we tested on a later version so it can work. And we recommend you to use the Art Studio so that you have like a dashboard to follow the ongoing process. So I will quickly describe the main functions that are used in the toolbox. There are 7 main functions that can be used that rely on other auxiliary functions. So the first important one is the initialize Argo functions that will define standard settings for the rest of the protocols and download and process the synthetic file profile index files. Then you have the load float data function that will load into the memory of your computer the data from one float or several floats if you choose to. Then select profiles, which is a function that allows to research the database to look for floats in a given geographical area or during a given time period. And finally, 3 functions to plot and to look at, to visualize the data. So first function to plot the trajectories of the profiles that you choose to look at. The second function, show profiles, which will plot the vertical profiles of a given parameters as function of the depth. And finally, show section function, which will plot time series of given parameters and selected floats. And finally, you will find the main workshop function, which is basically the tutorial function that we will use today, and that will go through the different previous functions. So to reference this toolbox, you have the README file where is detailed all the references and the DOI. And yes, keep in mind that this this package was recently developed and might still need improvements or adjustments. So feel free to contact us, to give returns. And so either using GitHub issues or pull requests to report any problems, any improvements that you think to, or directly sending an email to Yibinrong or myself. So just a quick reminder on how the synthetic file index and files are made. So S is for synthetic, meaning that all the cycles are merged in one file for a given WMO, and also that the core parameters, so pressure, temperature, salinity, and the BGC parameter are all adjusted on one vector of depth, one common pressure axis. And so in the repository, you can find either SR file, which means synthetic real-time files, or ISD file, which means synthetic delay mode files. And so just to give you a quick view of how the profiles file indexed file is made of, because it's the file that is used after to select the different parameters for each WMO, or each profiles. So what you first find is a link to the direct files. So you can see here the link to the GDAC repository. And after, for each profiles, we'll have information that are used within the further functions. So first you have the file path, which is composed by the DAC. So here you have example of AOML. Then you have the WEMO number, which is the ID of a float. Then you have the profile folder. And finally, you have the name of the file, which is composed by the WEMO plus the cycle number of the float. After, you have information of the geolocation of the profile, so the date, latitude, longitude, and the ocean. After, information on the float itself, and then you have a parameters vector, which gives you the parameters that are available within the profile. So here, for example, it's the pressure, temperature, salinity, and dissolved oxygen. And after that, you have a corresponding parameters data mode, which gives for each parameter the mode of processing. So here you can see that all the parameters are 4Ds, which means the 4 parameters are in delay mode. And finally, the date updates, which mean at which date the file have been updated. And so all this information are contained by the synthetic profile file index are used in the further functions. And just to give you a small reminder of the data modes that are available. So for each parameter, you can have three data modes. So the first one is R, meaning for real-time raw data. Second is A for adjusted data mode. And finally D for delayed mode data. And so note that for the Argo files, so for each profile file or the global synthetic profile file, you have only 2 data modes. So R for real time, that can include both raw and real adjusted data, and D for delayed mode adjusted. And finally, each file name has a data mode, and this data mode corresponds to the highest level parameter within the file. So now we will, just before to go through the live tutorial, just to remind that you can use the help desk. Either you can send a message here on the main chat asking for going to the breakout help room, and then people from the help desk will come to help you. Or you can use the Slack link that you have here and ask directly questions on the help desk. And so, yes, just to remind that these Slack channels will remain accessible after the tutorial session, and you can then continue to have access to to the information and ask for help. And now I will leave the floor to Yibin, who will drive you through the live tutorial. Thank you.
Can you hear me?
Yes, we can hear you.
Okay, great. Thanks, Maureen, for a very nice introduction. Good morning, good evening, good afternoon, everyone. My name is Yibin. I'm currently a postdoc at the NOAA Pacific Environmental Laboratory studying the marine biogeochemistry. My current research is using the multiple BGC flow deployed in the Southeast Pacific to quantify the regional biological pump. Then today I will walk through the demo in the following sessions. This demo includes the full example covering the flow data assessing, loading, processing, and visualization. My hope is this demo can provide you a better sense about what our toolbox looks like and how it can better engage in your current study. Before I get into this, I would like to go over the rule again. Please mute yourself, but feel free to put any question and comment you have in the chat board or the Slack channel. Our team member will stay online to address your question. Let's begin. Let me share my screen. Okay, can you see my screen?
Yes, we can. Thank you.
Okay, I will get started from the folder we download from the GitHub and open the script called the May workshop. Okay, let's get into the demo. So in this demo, the first place you need to do is to set the directory to the place where you put your code. Here it is. Because our toolbox will require some existing toolbox, therefore this step is to check whether these required toolbox are available in your computer. If not, it will automatically download from the website. Then we will load a set of functions we create in this toolbox. In the following session, I will review some of the important functions. Let's go into the exercise 0. The first critical function we create is called the initialize. This function is designed to download the global profile index from the global center as Mary introduced earlier. This function will take some moment to get it done depending your internet connection. Let's wait for 1 second. Yeah, it's done. After you run this function, on your right hand side, you can see the 3 new create variables. The first variable is float. This parameter includes the information such as the file path of each flow deposited in the global data center, what kind of the data center each flow belongs to. For example, the MOL represents the US Argo data center. This is the WMO ID for each flow. The latest date of each flow being updated, and how many profile each flow contains. Another useful parameter is called the S-plot. This variable tells us the information about the sampling day, latitude, longitude location for each profile, the ocean basin this flow operated, what kind of the parameter this flow measured, and its data mode. The third variable created is called the setting. It includes the setting to be used in the background for downloading flow data and plotting the finger. The host indicates the link for the two main global Argo data center. The first one is maintained by US. The second one is maintained by France. So when I download Argo data, we will first try to get it from the US data center. If it doesn't work well, it will shift to the French data center. Due to the time limit, I'm not going into very detail for this three variable, but I'm strongly recommend you to check it one by one. This is a good way for you to get a better understanding about how the data structure look like in the global data center. Moreover, the general idea in our toolbox to search our desired flow is just based on the float and the synthetic profile index shown in these three variables. Let's keep moving. The first exercise is to demonstrate an example to show you how we can get a basic information by the given flow WMO ID. For example, if we know one float WMO ID 5906439, either from the literature or from other study, then we can tell this WMO ID to the machine and then use this code to see the place where this flow was deposited in the global flow index. Here we can see that this flow was deposited in the line 545. The same idea, we can use the following code to check the place where the multiple profile of this flow were deposited in the profile index. Here we can see that the profile was deposited in the 7th place in the global profile index. Based use the place information, we can further to check the sampling day and what kind of parameter are measured by this float. Let's run this code. Here you can see that today this flow had measured the 6 profile. The first one was measured in May this year. The last profile just made 3 days ago. Then let's check what kind of the sensor this flow carried. This flow carries a bunch of sensors, including the temperature CTD to measure the pressure, temperature, salinity, and the school of the biogeochemical sensors such as oxygen, chlorophyll A, backscatter, pH, and nitrate. Let's move forward to the next exercise. In this exercise, I will take a recently deployed BGC flow in the Southern Ocean as an example to show you how we can download the flow data and then import into R and subsequently make some simple graphic by a given WMO flow ID. The WMO ID for this flow is 5904859. To download flow data, our team create a function called downfloat. Here is the instruction for this function. You can open it, this script. Here you can see that in this function, the only one thing you need to input to the function is just the flow WMO ID. For the more detail, you can check the following instruction. Let's go back to the example. So in this case, we input the single WMO ID and run the download function. Now we need to firstly tell the machine the WMO ID and run this function. If we are successful download the flow from the global data center, you can see on your right hand side, the success flag will turn to 1. Otherwise, the function will report the problem. Another thing I want to mention that this function can be also used to download the manifold BGC flow in the same time if you input a set of the WMO ID. Let's keep moving. Then we can use the NC open function to check the variable and the content in the netcdf. Here we can see this netcdf file include a lot of information such as the short name, long name for each variable, each unit, resolution, and the format. For simplify, we also create a very quick code to high-level check the variable in the netcdf file. Let's see how it looks like. Here we can more clear to see that this NC file include the information such as the date when this file was created, the people who are responsible for this flow, the cycle number, what kind of the data center this flow belongs to, the mode of this flow, the sampling day, and a bunch of the physical and the biophysical parameters such as the temperature, salinity, oxygen, chlorophyll A, and so on. For example, the nitrate here represents the nitrate without any adjustment. The nitrate adjusted represents the nitrate data after the strict QC control. And its corresponding QC flags are put in this variable. To more easily input this NCNet data into the R, we design a function called load flow data. Let's see the instruction. In this function, you require to input the flow WMO ID. If you didn't specify the variable, they will input all of the parameters available in the netcdf file. But if you specify, they just import the parameter you are interested. In addition, we provide an argument called float profile. If you just want to see the specific profile rather than all of the data, you can tell the machine the detailed flow index. In this case, this function just input the specific profiles. In this exercise, we just input the single WMO ID. As you can see in above, this float carry the nitrate sensor. So in this case, we just want to see the salinity, temperature, and the nitrate, and specific to the variable argument. Let's run this function. Just wait for 1 sec. Yeah, it get it done. Here we set the float data to deposit in the parameter called data. On your right hand side, the data has been successfully input into the R. Then we can use the following function to quickly check what kind of parameter has been imported into the R. Here we can see that the input variable including the cycle number, sampling date, pressure, salinity, temperature, nitrate, and with different data modes and their corresponding QC flags. Another very useful function we created is called the show trajectories. The only one thing you need input into this function is also the float WMO ID. Then it will continue to create the map for the float. The same will also provide the argument plot index if you just want to draw the specific profiles. But if we didn't specify that, the function will automatically plot all of the profile. For more information for the float, for the function setting and the instruction, you can check this instructions. In this case, we also just input one single WMO ID. Let's see how the float trajectory look like. The same with the download function. In this function, you can also input a manifold WMO ID, so it can also plot the manifold float trajectory with the different colors. Here you can see the float trajectory. On the right hand side, the legend indicates the WMO ID. It's a quite convenient function. Keep going. The shoot profile function is used to plot the profile. In this function, you also require to input the float index and as well as what kind of parameter you want to plot. In addition, we provide a different argument for the finger plot. For example, the argument type is to tell the machine what kind of the float index you input. If you put the float index, you need to set the type to float. On the other word, if you put the profile index, you need to set the type to profile accordingly. The argument OBS is to tell the function whether you want to plot the point in the profile at which where it was measured. The argument QC flag is to tell the function what kind of the QC level data you want to plot. As you know, in the Argo data, we clarify the QC flag from the 0 to 9. The flag 1 represents the good data. The flag 2 means the probably good data. You can check the more detailed information for the QC flag in this literature. The argument law is to tell the function whether you want to show the adjusted or unadjusted data. The default setting for law is no, which means the function will plot the adjusted data. The method is used to tell the function whether you want to plot the mint profile or the maniple profile. You can also choose to input the title for this finger. The float argument is to tell the function whether you want to put all of the float in the single finger. Let's go back to the exercise. In this case, we input the float WMOID. Correspondingly, we need to set the type to floats. In this case, we are just very interested in the salinity and the nitrate, so we specify the variable setting. We set OBS to on, which means the function will show the point on the profile at which each measurement was made. The law was set to be yes, which to tell the function we are going to show the unadjusted data. Let's see how the unadjusted salinity and the nitrate look like. On your left-hand side is the salinity profile. The red line represents the mean profile. On your right-hand side is the nitrate profile with the unadjusted data mode. Here you can see that the nitrate profile seems very divergent. There are some profiles are apparently derived from the maniple nitrate data. This is because this is an adjustment data without any QC. Let's see how the addressed salinity and nitrate will look like. As I mentioned earlier, the default setting for the law is no, which means if you didn't specify the law, the function will directly plot the addressed data. So in this case, we didn't specify law. That means the function will show the addressed salinity and nitrate. Let's look at the difference between the adjusted and unadjusted data. If we firstly look at the salinity, it seems that there is no apparent difference between the salinity in between the adjustment and unadjustment. This is because for the physical sensor, it requires the less calibration. However, for the nitrate, it seems that the adjusted nitrate showed a little bit better than the unadjusted nitrate data. But here you can see that there are still some very weird profiles. This is because even though it's adjusted data, we include different QC level. We probably also include the back data. So let's see whether the nitrate profile would look normal if we set the QC flag to be 1 and 2, which just tell the function we just plot the good or probably good nitrate data. Well, here you can see that the high quality nitrate data, the profile look quite normal. This example also reminds us, especially for the biochemical parameter, only delayed mode with the QC flag being 1 and 2 can be used for your scientific research. Let's close the finger and move forward to the next exercise. The shoot section function is used to plot the trajectory for the given variable. The same with the shoot profile. The one you need to input into this function is the float WMOID, and you also need to specify what kind of variable you are interested. In addition, we provide the different option for the finger probe. The probe isopinal depth is to tell the function whether you want to probe the isopinal depth. The probe MLD is to define what kind of method you want to use to calculate the mixed layer depth. The setting 1 means that we will calculate the mixed layer depth based on the temperature threshold. Setting 2 is to calculate the mixed layer depth based on the density criteria. If we set to 0, the function will not plot the mixed layer depth. We can also to set the maximum depth you want to plot. We also provide the raw OBS QC flag argument in this function, which I had introduced in the last function, so here I'm not going into the detail. In this exercise, we also input the single WMO ID and just want to plot the nitrate variable. We set the plot MID to 1, which means the function will calculate the mixed layer depth based on the temperature threshold. We set the raw to yes, which means we will show the unaddressed nitrate data. Let's see how the transaction look like. Here is the image. The x-axis is the time. You can see there are nearly 4 years data from 2017 to 2021. The y-axis is the pressure. The black line is the mixed layer depth. The red line is the isopinal depth, with the corresponding density number shown in the label. The color represents the unaddressed nitrate. The second example is to show the address data by setting the argument law to no. The third one is we further specify the QC flag to 1 and 2, which means the function just plot the good nitrate data. I just directly switch to the third example to see the nitrate transaction with the high quality. Here you can clearly see that the high quality nitrate data are only available before 2019. After that, there is no high quality data, even though we have nearly 4 years observation. Let's move forward the second exercise. In this exercise, the aim is to provide you example how to search the flow data according to the temporal and spatial boundary. I think this example will be very useful, especially at the beginning of your study to search the flow you are interested. To do this end, we create a very smart function called the select profile. Let's see the instruction for this function. In this function, you need to input the longitude, latitude boundary, the time coverage, including the start date, end date. You can also to specify the sensor you are interested. If you didn't specify it, they will search all of the BGC flow data regardless what kind of the sensor it carried. The argument outset is to tell the function whether you want to retain the profile of this float. as long as there is one profile falling into our temporal and spatial boundary. In this example, we want to search the BGC flow near the OSP during the period from 2008 to 2018, nearly 3 years. And we are hoping to get the nitrate data. The first step, we need to set the latitude and longitude boundary, which is about 3 degrees central to the ocean station P. Then set the starting date to the first day of 2008, the end date to the last day of 2018. In the input of the select profile, because we just want to search the BGC flow carrying the nitrate sensor, therefore we specify the sensor parameter to nitrate. We set the outside to both, which means we will search all of the BGC profile of this flow as long as there is one profile falling into our spatial and the temporal boundary. The searching result will be deposited in the OSP data. It has shown on your right hand side. Let's see how the result look like. The first part is tell you the flow index you obtain. The second one is the flow index you derive. Then you can use the following function to see how many profile and float which are agree with your requirement. Here we can see that we get more than 18,000 profile which meet our requirement and 7 BGC float in total. Then we can use the function called show trajectory to plot the flow pathway for this manifold BGC flow. I run this function before I mention it because it required a long time. It needs to download the flow data first and then input the data into R, then subsequently plot the finger. Because we have a 6 BGC flow, so that is a long time waiting period. In this case, we improve the access of the flow WMOID. While waiting, I want to say, please feel free to put any questions you have in the chat box. Our team member are very happy to address this question. In addition, another point I want to emphasize is our toolbox is still in the active phase for the code development. So there are probably some problem and unsolved issue. So any comment and suggestion are also welcomed. You can either send the problem and comment via email, or you can support the pull request in the GitHub. If you are also interested in join our team to further perfect the toolbox, it would be really welcome. You can contact us. Let's wait for 1 more minute to get it done. Take a very small break. The code speeding also depends on your internet connection. Yeah, here we go. Here you can see the manifold flow trajectory near the OSP with the different color represent the different flows. Then you can continue at the black box to show the domain you are interested. Here is the image. Let's continue. In the next example, we will continue to plot the profiles for the first BGC float we get. In this case, we want to plot the salinity and the dissolved oxygen. Again, because in the first place, we put the WMO ID, therefore, we need to specify the type to flows. To tell the function, we are input the float ID rather than the profile ID. We set the OBS to on to tell the function to show the point on the profile at which each measurement was made. Yeah, on the left-hand side is the salinity profile, right-hand side is the dissolved oxygen. The only one different for the second case is we specify the argument method to mean, which means this function just plot the mean profile from the manifold observation. Let's see how the mean profile look like. The black line represents the mean derived from the manifold profile, and the blue line represents the standard deviation. This is all for the exercise 2. Regarding the exercise 3, is quite similar with the exercise 2. It also show you example how we can search the desired flow based on the spatial and the temporal restriction. In this case, we want to search the flow near the Hawaii from 2017 throughout the 2019. Here we didn't specify the sensor. We are hoping to search all kind of the BGC float operating around Hawaii, what kind of the sensor it carried. The first step, you need to set the geolocation boundary as well as the temporal coverage. Then use the select profile to search our desired float. Here we set the argument outside to null, which means this function only search the profile of this flow which are within our temporal and spatial boundary. Let's see how many profile and flow we get. The same, use the following code to see the number and the profile. In this case, we get about more than 200 profile and 5 flow in total. In the following example, it just continue to show the trajectory and the profile, which are quite similar with the last example, so I'm not want to show it once again. But the only one example I want to demo is in this case, we improve the float, we improve the profile index rather than the float index. Because in this example, we just want to see the profile measure in the September. Therefore, the first step we need to do is to search the profile index, which are measured in September. Here we can see we get the place information where the corresponding profile were deposited in the global profile index. And then in this case, in the pro ID variable, we include the profile index. Correspondingly, we need to set the type to the profiles rather than the flow as we show in the case above. Because this flow index includes a manifold BGC flow, therefore we specify the per float argument to 0, which to tell the function we want to show the all profile from the manifold float in the single finger. Then we specify the QC flag to 1 and 2, which means we just show the address data with high quality. And add the title September in the finger. Okay, this is the last example we want to show. The following is continue to show the transaction, I think, which is pretty similar with the example above. I hope this demo helps. Okay, I finished my own part. Mary, do you have anything want to add?
I know it was for me it was great. You doing great job.
How many minutes we left right now?
I think we got a message that we should go back to the main meeting at into 3 minutes now.
Yep,
Oh.
and they'd like everybody there for a noon start, so maybe a 1 minute or so wrap up and people can head over. Quick bio break if you need. Thank you.
So is there any specific question, Maureen, you want to mention or want to initiate some discussion before we end up this session?
No, I was thinking there is no message on the help desk, but maybe the channel can stay open after the meeting so that people can ask question and we can look at it after and provide help maybe.
Great. Again, thanks for everyone joining us. So our toolbox, as I mentioned, is still in the active phase for developing. So any questions and comment are welcomed.